Okay.
We are live.
We are live.
And I am the cameraman.
So don't make problem number one complicated in terms of you're drawing the superposition of the waves.
Which
okay?
one? I'm just kidding. I already talked.
Huh?
Oh, I did it right.
Never mind. Just ignore what they just said.
So basically, you've got these waves coming in, and they're going to begin to interact. So there's a couple of things that you need to keep in mind. First off, if the waves have it, if you look at where this leading edge is, and it's the second one and the fourth one get a little bit dodgy. Because if you look at how fast they're moving, they kind of have this scale drawn. So when you get to the second one, and what I did here with these dashed lines is saying, okay, this is where these waves actually are. So if you come in here and you like added them together, so you'd have basically this little bit here added with that little bit here, and you're going to end up with basically a horizontal line. And the same thing here, because you're adding, if you look at what's going to happen in the middle, you're adding, like, in effect, the two halves. So those two halves would add up to get you basically like a horizontal line across here. In that third one, this is where they're completely on top of each other. Okay, they're completely superimposed at that point. So when they're completely superimposed at that point, that's when you're going to get that big maximum amplitude. Okay, and then the fourth one, they're starting to pass through each other, and then the fifth one, I think that's when they're like completely separated and they pass through each other. So here's what's important: is that there's like two waves passing in the night. They interact while they interact, but afterwards the waves just continue on just like they were before. Okay, so there's no like residual glow. I lost part of that energy. Anyway, so that's kind of all I'm looking at on there. Typically on the test, they just want you to know, hey, if they're both the same amplitudes, they get added up. If you have like a trough and a crest, then they're going to cancel each other out. I mean, that's kind of the extent of to what you need to know with that.
You want the vectors on there as well, of the direction they're moving?
Yeah, you just have to put them on all of them, just at least at the beginning, so I know which one's going in which direction. Okay, that's it. So let's talk about
7B.
Well, we'll get to that. So let's talk about question or problem number 26. Okay, the Parasalopoulos. This is why I didn't study that, because I can't pronounce Latin words. So anyway, so they're basically telling you, as an open closed system, what are the first three resonant frequencies, assuming the speed of sound to be 350 meters per second. So on this one, on 26, because it's like an open closed system, and this is the whole point of the lab today. Basically, you're assuming that the length of that is what's called the first harmonic, which is the fundamental frequency. That's going to be 1/4 of that wavelength. So once you get that wavelength, then you can figure out the frequency. So to find that first harmonic on 26, you assume that this is 1/4 of the wavelength, which is like, this whole length here is 1.5 meters, which is pretty impressive. I mean, you consider 1.5 meters is about like yay, okay? You consider that's like, the nasal cavity on this dinosaur. It's pretty big, T-Rex. Okay? And so when you find that first one, you basically, to get the wavelength, you're going to take 4 times 1.5. That's going to be your wavelength. They've given you the speed of sound, which is 350. You can find that frequency. Okay? Smash mouth, take 350 divided by the wavelength. Boom, there's your frequency. Because it's an open closed system, your next harmonic is going to be like 3 times that initial frequency. Okay? So that first frequency should be around 60. That's an ish. Okay? But it's going to be something around 60. So then the next resonant frequencies is going to be 3 times that. And then the next one after that is going to be 5 times that. On open systems, you go 1, 2, 3, 4. On open closed systems, you go odd numbers 1, 3, 5. I'm not really going to expect you to know that, okay? but you do kind of need to know like the terminology. So like if you have a standing wave, okay, this is what's known as the fundamental wavelength, because this is as simple as it can possibly get. Then the second fundamental would be something like this, where you actually have that wavelength within that system, okay? And then the third one would be, you know, then where you get something weird like that, okay, which is why this, because it's like this part of it, and that's why it goes on the third harmonic, where, because that's going to be the next part of that, where you end up with a closed, with a node here, an antinode, an antinode, and a node, and that's where you end up, why it goes 1, 3, and 5, but with an open system, it goes 1, 2, 3, 4. Okay. Anyway, your answer to 22 should be around 400. Your answers to 20, the first answer should be around 9, and the second answer should be around 4 or 5. Okay. Now, Ryan, which one did you ask?
7B.
On the question or the
Yeah.
problem?
The question.
Okay. So,
I can see justifications for both. It's basically just your terminology.
well, here's the deal. So, you got a standing wave, right? Okay? So, even though we represent it as a transverse wave, what type of wave is sound wave?
Get the name.
Starts with an L.
Linear?
Close. Longitudinal wave.
Okay.
Okay? So remember, on a standing wave in a
So-
tube, because it's a longitudinal wave, okay? So with that, these compressions and rarefactions are actually establishing a resonant structure within that. Graphically, we draw it as a transverse wave, because it's really tough to draw compressions and rarefactions within a tube, okay? But it's pretty easy to draw, oh, here's half of the wavelength. So that's the dichotomy, is that we draw them, so we draw sound waves like they're transverse waves, but in reality they're longitudinal waves. Because to really draw this, like in this system, you'd have like a bunch of air molecules close together, then you'd have a big gap, and then you'd have another bunch over here, and then you'd have, you know, it'd just be weird, okay? And so that's why we go, oh, let's model it as a wavelength, as a transverse wave, when in reality it isn't. But it's the same thing, it's the same wavelength, it's the same frequency. We just draw it in reality that makes it easier to look at. So, okay. Yes?
Number 8.
Problem?
Yeah.
Okay. So, here it is. So, you got typical flute, right? Piccolo's very similar. How does the pitch look compared to that? Oh, no, I'm looking at problem number 8. Sorry, I was looking at question number 8. So, here's the deal. So, you're 3 meters away, right? So, and you begin shaking it, okay, create a continuous sinusoid of wavelength 1 meter. So here's the deal. So within this, so this whole thing is like 3 meters. And you're going to have a wavelength of this. So look at it this way, okay? You're 3 meters away. So how far does that wave have to go to get in?
3 meters.
How far does it have to go back?
3 meters.
Okay, so that's going to be your total distance, okay? So then, if you know that it's going to travel that distance and you've got your frequency and your wavelength, so as soon as you have your frequency and your wavelength, what can you find? If you multiply frequency times wavelength, what do you get?
Velocity.
Yeah, and you know it travels a total of 6 meters.
Just divide that by.
Yeah, find your speed and divide the 6 meters by that. Okay. So your answer, your answer to number 8 would make a horrible GPA. All right, anything else?
Your GPA.
Once, twice, sold. Okay.
What is that? That's the end
Now, we deploy something this has.
Today's story is
Your GPA is not applicable.
that is
I realize it I am not a bright person.
Oh,
I mean, it's stupid.
Young man. Hi. How you doing?
Disc and washer method is
Young man.
an hour and a half straight.
They're thinking of putting in a light at 37 pilot.
That's what they're talking about.
I like the that was one of the things they were talking about. Right? They're like, well, you know,
Right. I'm below.
There's only traffic during the.
People also don't know how full it's off.
Oh, it's on the no one knows how far. Bro.
Should
we have a strike for the disadvantage? So there's your motion strike.
She can't feel herself. She can't.
I guarantee you, anybody who's ever taken calculus 1 or 2 to like it's that's a nice.
Specifically the washer.
Oh, watch my
Do that. You're and then
I'm so glad we're not what shell methods really powerful too.
We're doing that.
Nobody's never made it.
No, you're gonna do that.
I don't think we're doing it.
No, Ryan, you need to use your shoe.
No, it's just because you're probably gonna have it on like the test. Like you use the shell method. Oh.
I think an absolute
Don't say that about her.
What is L?
I know a guy who
over seat stuck to the back of my backpack.
No,
Is it the link of the graduated cylinder? All the Huskies is another graduated cylinder. I don't know what else.
you would never guess that by looking at it.
I would not. I would never.
D is diameter.
I don't think
It's the length of
I'm
pipe.
assuming it's the length.
What?
I don't know. I'm sure he'll explain.
Oh,
There's like two and one.
To use in the.
Oh, yeah, that's 1 meter.
You needed to do this.
Unless you had like.
Another 10 meters.
The slope, the line change in the temperature.
No, this is.
Explain.
Okay. Well, I can't find it. All right, so let me explain. There's going to be two parts to this lab. Okay? So 3 of the four of them are going to deal with an open-closed system. And one of them is going to deal with an open-open system. So the open-open system is actually the hardest one to hear. So this one I'm actually going to set up in the other room because that way it's easier to hear. Okay? So what you want to do, and again, do not, you can hit these on the palm, you can hit them on a book. Do not hit these tuning forks on a hard surface. Okay? So you can hit them on your heel. Okay? So this is where you got to have, this is kind of a two-person operation. So within this, there's an inner tube that you can slide. That's what's going to allow you to adjust the length of this. So you hold this, okay? You just hold that. So I'm going to get this thing going, okay? And then I'm going to get him to pull this out. And you're going to reach a point where it becomes pretty loud, okay? That's the length that's going to be that resonant structure. So what you're going to need to do is measure like the length from this end of the tube out to here. And then what you're going to do is going to use that as a basis to try and get an estimation of the speed of sound based upon this. Because you're going to know the frequency of the tuning fork. Okay, you got this number. You're going to know the length of an open system. Okay, so you're going to have this number. And then from that, you're going to try and figure out the speed of sound. So that's going to be on the open one. The other ones are going to be on an open closed system. So with this one, so this particular one is an unknown. With this particular one, what you're going to know is you're going to know the speed of sound, which we're going to calculate in just a second, because you have to take the temperature into account. So with this one, okay, okay, so you're going to find that point where it reinforces, and then you're going to measure the length of this column. So then what you're going to try and do is figure out what the frequency of this tuning fork is based upon the speed of sound. The other three, you're going to try and calculate the speed of sound, knowing the wavelength and the frequency. So on the other three, which are the open-closed systems, and you're going to have like basically 4 stations set up. I'm going to have one here, which is going to be the unknown, and you can rotate around. So you're going to have one here, one back there, which is going to be known one, another one in the back, another one over there. And then the open system I'm going to have over there, so that one's kind of the hardest to hear. The other ones are pretty easy to hear. It's the open system that's tough, okay? Now, so here's the deal. So when you look on your lab, so right now, we need to figure out what we're going to use as the accepted value for the speed of sound. So down here on number 9 says determine the accepted value of the speed of sound from the following equation. Okay. So right now we are at 21 degrees Celsius. So we're going to make sure everybody's on the same page. So down there on number 9, we're going to take 331 plus 0.6 meters per second times 21 degrees Celsius. So somebody take 331 times, and then add that to 21 times 0.6.
343.6.
So call it 344. So that's what we're going to use as the accepted value for the speed of sound. So if you go through here, the other thing that we need to do, and up there on this third line, we need to have a corrective factor, because what happens is that as these waves actually come out, because they're confined within a tube, they actually expand, so you kind of get a false reading. So what your actual wavelength is going to be, so, and there on line 2, I've got lambda equals 4 times L plus 0.3 D.
That's the diameter?
Yes.
Okay.
That has to be the diameter in meters. Okay? So most of these all have the same diameter, but you kind of might visually check, make sure nothing's wonky. But you only have to do that on the open closed system. You don't need to do this with the open system. Okay? So for example, like what you're going to do with that unknown one, you're going to know the wavelength, okay? Then you're going to know the speed of sound, which is what we just found. And then you're going to try and solve for the frequency. So over here on the second page, on that unknown, this is the section where you're going to do the calculations to try and figure out what the frequency of the tuning fork is. So up here, over here on page 2, this is where you've got all of your data. So you're going to have, I've told you specifically what the 3 frequencies are, 324, 26.6, 512. You're going to take 0.3 times D. The L is what you're going to measure. Now, the length can get a little bit sketchy, okay, in terms of what you're going to measure, because you've got to have somebody hold this up, and then you've got to measure from like the top of that tube down to the surface of the water. So this is why it kind of takes a couple of people to do this lab. That's going to be, don't try and like, you can stick the meter stick in there to the edge of the water, but all that's going to happen is just going to get it wet and bad things are going to happen. So I just measure this distance out here, measure the diameter of the tube, okay? And that's the inside diameter of the tube, not the outside diameter of the tube. That's going to be the inside diameter of the tube because that's where that air is going to be escaping from. So don't measure the outside diameter of the tube, but measure the inside diameter. So then when you get done with all of that, so we've got the air temperature, theoretical value of the velocity. We've already done that calculation. So what you're going to do is that you're going to calculate the speed, and then you're going to calculate the experimental error. I don't have to see all the calculations of experimental error, but at least show me one of them, okay? At least show me one calculation of your experimental error, because remember, that's theoretical minus experimental divided by theoretical. So in this situation, we should get 344. So you're going to take 344 meters per second minus whatever you get divided by 346 times 100.
Ah, yes.
Okay? So then you've also going to, down here on this front page, on line 13 it says plot a graph of frequency versus the inverse of wavelength. Okay? So you're going to have 3 data points. Okay? You're going to have frequency versus the inverse of wavelength. Then you're going to calculate the slope of the line, pay attention to what the units are. Okay? And then what physical quantity does the slope represent? Okay? And then I'm going to ask you, hey, how the slope of the line changed if the temperature had been much colder. So in other words, go back, when you answer number 16, go back and look at how we calculated the airspeed. If the temperature of the room had been like 10 degrees Celsius, what would that do to the theoretical limit of, what would that do to the speed of the air? Or the speed of sound in that air? And then how would that impact the slope of that line? Okay? Then you've got these questions to answer. This is from the 2015 AP test. So let me kind of give you kind of a visual. So basically, you've got an oscillator, which is going to generate like a standing wave in here. And then you can hang different masses from the end of the string, which is going to alter the tension in the string. Obviously, the more weight that you hang from the end of the string, the more tension that you're going to have. And they've given you this formula that you already, this very first formula on this page, you've already actually dealt with that. It's that velocity equals tension, and they actually listed it as tension divided by ml. When we went over it, we had it as tension divided by mu, and mu is that mass per unit of length. So they just went ahead and listed it as mass divided by length. When you all did it, you did that as mu, which is the exact same thing. So they just said, hey, we're just going to put this as mass per unit of length. Okay? So break up into different groups. So you don't have to do this in any particular order. Okay? It doesn't matter. So like I'm going to take the open one and put that over there. I'm going to have the 4 open closed systems here. What you want to do is, what I would recommend is that you kind of find that point as you lift the tube up, and then compare that to what's going to happen when you lower that tube down. Hopefully those 2 points should be about the same. So take your time. We're in no big hurry. You have to get good data. Okay? All right, so